The Hubble Rift. 2 clocks, 1 universe. 2 clocks are arguing across the sky. One is the early universe clock, read from the faint static of the cosmic microwave background, the afterglow mapped with Planck satellites and ground arrays. The other is the late universe clock, built from exploding stars, lens galaxies, and calibrated distance ladders. They're both precise. They won't agree on how fast space is expanding right now. Start with the early clock. Planck measures tiny temperature ripples frozen when the universe was hot and dense. Feed those ripples into a well-tested model. Dark matter scaffolding, dark energy pushing, normal matter glowing, and you get a tight prediction for the Hubble constant. It's careful, global, averaged over the whole sky. That clock says today's expansion rate should land at 1 number. Meanwhile, across town in astrophysics, the distance ladder crew does it differently. They build a chain. In our cosmic backyard, parallax gives hard distances to nearby stars. Those stars calibrate Cepheid variables, pulsing beacons in other galaxies. Cepheids calibrate type Ia supernovae, standardizable candles bright enough to see far out. Stack the rungs, measure redshifts, and you get a direct local expansion rate. That clock lands higher. The 2 error bars used to overlap. They don't now. Why it matters isn't a pedantic constant fight. Expansion sets the scale for time and distance in cosmology. It decides how old the universe is, how structure grew, how galaxies assembled, and how dark energy behaves. If the clocks won't sync, either something subtle contaminates a measurement, or the model tying early ripples to today's pace is missing a piece. Both options carry a price. Here's the human version. Imagine groups that have spent a decade shaving uncertainties, building better detectors, revising calibrations, arguing with their own data until the numbers hold still. Careers hang on those decimal places, funding bets on them. Conferences turn into careful cross exams. Nobody wants a phantom. Nobody wants a fudge factor. They want the tick to land. Call it a desync. The early clock is like a timestamp logged at universe boot, extrapolated forward through the rules. The late clock is a timestamp stamped on today's screen, averaged over countless local patches. If the rules are perfect and the bookkeeping is clean, they should match when you account for noise. They don't. The mismatch has persisted through new instruments, alternative candles, and revised priors. What nobody knew at first was how sticky the rift would be. Blame shifts. Maybe Cepheids are trickier than we thought. Dust, metallicity, selection bias. Teams swap to other rungs, tip of the red giant branch, masers, time delay lenses, and still find high values. Maybe Planck's inference depends on the assumed recipe of the early universe. People try tweaks, extra relativistic species, early dark energy, sterile neutrinos, changes to recombination. Some soften the rift, most
create tension elsewhere. Fix the early clock, rip the stitching on nucleosynthesis. Fix the late clock, break large-scale structure growth. This is where the budget theme peeks through. 2 ways of telling time. Global compression of ancient information versus local high-fidelity snapshots are returning different answers. If the universe prioritizes consistency under finite information, there's a trade-off hiding here. The early universe read compresses everything into a few parameters with small errors. The late universe read gathers many heterogeneous samples with complex systematics. Each method spends its precision budget differently. The disagreement looks like the cost of reconciling 2 compressions. Meanwhile, instruments push harder. Supernova teams chase better 0 points with space telescopes, avoiding atmosphere and dust. Planck's successors, ground-based CMB experiments, dig into polarization and small scales. Lensing surveys weigh the cosmic web. Radio arrays time pulsars to build a gravitational wave background clock. The more clocks we set, the more we expect convergence. The irony is, we're now precise enough to force a choice: new physics or a subtle global error. Here's a micro story. A grad student spends nights aligning supernova light curves, watching the stretch and color corrections snap into place. She moves 1 calibration star from the sample and the Hubble value shifts by a whisper. She moves it back. The whisper returns. It's not enough to save the truce. In another building, a theorist adds an early dark energy term that briefly accelerates expansion before recombination. The early clock ticks faster for a moment. The late reading relaxes toward it. But the change drags on other data like a snag on a sweater. While that's happening, statisticians comb for human bias. Are teams unconsciously herding toward their priors? Blind analyses help. Pipelines hide the answer until methods are locked. Results still split. The rift resists personality in pipeline. It starts to feel like a real seam. There's a quiet psychological cost. If the second you trust is defined by models, and those models disagree across epochs, confidence thins.
You still fly satellites, still map galaxies, still calculate orbits, but a question hums beneath the calculations. Which clock are we living on? Framed this way, the Hubble Rift is a global version of clock drift, a universe-scale desync between two impeccable metronomes. It doesn't mean the system's failing. It means we're at the edge of a budget where assumptions matter. Either the rulebook needs an extra page, or one of the clocks is reading through glass we haven't cleaned yet. And when you zoom smaller, the timing cracks whistle. Muon G-2, the particle that won't behave. Shrink the frame from galaxies to a single particle that lives for 2 microseconds and still manages to throw shade at our rulebook. The muon is a heavier cousin of the electron. Same charge, same spin, just bulked up. Put a bunch of muons in a magnetic field and they precess. Their little internal magnet wobbles like a spinning top. The rate of that wobble is g. In a perfect interaction-free world, g would be 2. Quantum fields crowd the scene, so the true number is G2, a small deviation that encodes everything the muon feels from the vacuum. Here's why this matters. That tiny wobble is a referendum on the standard model, our best set of rules for particles and forces. If G2 lines up with predictions, the book holds. If it doesn't, something unseen is tugging on the muon. New fields, new particles, or a flaw in how we're summing known effects. The stakes aren't abstract. Every proton in your body is accounted for by that same framework. If the rulebook bends here, everything compiled from it inherits bugs. The human moment is late nights at Fermilab, a ring the size of a skating rink, humming with magnets, and teams timing decays down to nanoseconds. They inject polarized muons, watch them orbit, and count the electrons that spray out when muons decay, because the direction of those electrons tracks the muon's spin. The frequency they extract is the wobble. An anomaly pinned to the 4th decimal place means months of calibrations, alignment, field maps, and cross-checks. You don't get to cry new physics because a cable was loose. Meanwhile, theorists fill blackboards with the contributions that add up to the prediction. Quantum electrodynamics piles on precise terms, photons flitting in and out of existence. The weak force adds its whisper. Then come hadronic effects. Quark-antiquark pairs bubbling in the vacuum, gluons tangling, the murky domain where QCD's grip is strong and calculations get hard. You can estimate those hadronic terms 2 ways. Use data from electron-positron collisions to feed a dispersion relation, or simulate QCD on a lattice with supercomputers. For years, the best consensus leaned on E plus E minor data. The old story from Brookhaven was a hint. The measured G2
was higher than the standard model prediction, a few sigma off. Not a discovery, but a nudge. Fermilab rebuilt the experiment, moved the Brookhaven ring, and pushed uncertainties down. Their first and second runs strengthened the tension with that E plus E minus base theory. The wobble refused to settle. Press headlines flirted with cracking physics. Inside the field, nobody popped champagne. They tightened bolts. Then theory moved. Lattice QCD calculations matured, and in some results, pushed the predicted G2 closer to the experimental value, shrinking the gap. That sounds like a rescue, but it shifted stress onto other observables. Hadronic vacuum polarization influences not just G2, but also how the fine structure constant threads through other precision tests. Make G2 happy with lattice, and you might upset E plus E, minor cross-sections, or electro-weak fits. Fix a tick here, stretch the ledger there. It's a familiar theme, budgets and trade-offs. This was the moment everything changed in tone. The anomaly wasn't a clean banner for new physics, but it wasn't dissolving either. Instead, it became a stress test for our entire modeling stack. Detectors, magnetic field uniformity, pile-up corrections, beam dynamics, decay asymmetries, and on the other side, multi-loop QED, hadronic light-by-light scattering, data-driven integrals, lattice systematics. Every layer carried an error bar that had to be paid for. Here's a micro-story. An accelerator physicist sits with coffee gone cold, comparing 2 independent field maps of the storage ring. One map is based on trolley probes that ride inside the ring. The other relies on fixed probes stitched together with a model. The difference is tiny but correlated with temperature. They rerun the analysis with a corrected drift. The central value shifts by a hair. The uncertainty narrows. The headline number barely moves. The wobble is still obstinate. What nobody knew at the time of Brookhaven's first hint was how much the conversation would pivot to hadronic light-by-light scattering, a notoriously tricky contribution where 3 photons dance around a quark loop.
Different modeling approaches give slightly different answers. Lattice is starting to weigh in. Each advance reduces wiggle room. If an unknown particle were boosting G2, it'd likely show up elsewhere. Rare decays, colliders, cosmology, the hunt widens, the cost climbs. So where's the seam? If you read G2 as a bill, it's a receipt for vacuum complexity. The muon's wobble integrates over everything that can couple to it, from the clean QED fringes to the messy hadronic soup. Our predictive power depends on how we compress that soup. Data-driven shortcuts versus first principles computation. The disagreement's persistence looks less like a magic trick and more like a budgeting problem. Precision spent unevenly across methods and measurements, and that ties back to time. These rings are clocks. The precession frequency is a timing signal born from quantum fields. When your clock won't align with theory's tick, you either miss the gear or there's a new cog in the machine. Labs keep refining the gear train, theorists keep redrawing the diagram. If the rulebook bends, the bend is small but consequential. A hairline that propagates. Bugs show up in networks too, at cosmic scales.
Fast radio bursts and rendering spikes. Now listen for the universe clearing its throat. In 2007, while combing old pulsar data, astronomers found a millisecond-long ping so bright it shouldn't exist. Then another. Fast radio bursts, FRBs, land like camera flashes from deep space. In a few milliseconds, they pour out more radio energy than the sun emits in days, then vanish. Some never repeat. Others stutter, then rest, then fire again. The sky is quiet until it isn't. Stakes first. When a burst hits, telescopes swing, pipelines trigger, and people sprint. The dispersion, the way higher radio frequencies arrive earlier than lower ones, acts like a yardstick for distance. The more the signal is stretched, the more plasma it crossed. Many FRBs look extragalactic, even intergalactic. That means the engine lives in extreme fields. Compact objects, magnetars, neutron star mergers, maybe exotic plasma shocks. It also means the event is brief yet information dense, an entire story told at once. Action is messy and thrilling. A burst pops in a survey instrument, say Kaime's Wide Field Radio Array, and software screams. Within seconds, automated alerts ripple across a network. Observatories in optical, X-ray, gamma rays, even neutrino detectors check their buffers. Did they see anything coincident? Sometimes a repeater gives mercy. It fires again. Teams triangulate with interferometers, nail a host galaxy, and zoom in on a star-forming knot. Magnetar flares become the leading suspect, especially after a galactic magnetar produced a FRB-like event. But there's variety. Some bursts seem too bright, too structured, too patterned for a single template. Like seeing multiple compression algorithms in one data stream. Here's where burstiness reads like load spikes. In computing, most of the time your system handles steady traffic. Then a surge hits, flash sale, breaking news, a bot swarm, and queues swell. You drop detail, buffer, or you fail. FRBs feel like cosmic queues emptying. A magnetar's crust cracks, magnetic fields reconnect, and energy that's been bottled in complicated twists seeks a cheap exit. The universe pays down stored complexity in a single clean blast. Compression in, sudden decompression out. Meanwhile, multi-messenger coordination is our stress test for reality's bandwidth. A gravitational wave alert from LIGO pings phones. Kilonova teams scramble telescopes before the glow fades. Neutrino detectors post a candidate. Gamma-ray satellites scan Earth's limb. For far Bs, the window is punishing, milliseconds, but repeaters buy time. When a repeater flares in a quasi-periodic way, scheduling locks in. Then the burst shows substructure. Microsecond spikes stacked in a drifting pattern like a chirped signal. Plasma lensing could explain it. So could emission regions sweeping across our line of sight. Either way, the data rate is insane. Instruments are pushed to dump buffers faster, clock stamps tighter, and still some frames smear. Impact lands in two places. First, astrophysics gets a new ruler. Average the dispersion across many FRBs, and you map the missing baryons in intergalactic space, the faint plasma that hides between galaxies. Second, we confront a cadence problem. Most of the universe is slow. Stars breathe in hours, galaxies evolve in eons. FRBs, pulsars, and magnetars jam speed into the timeline. They force us to sample fast without drowning in false positives. Every extra millisecond of timestamp fidelity costs hardware, power, storage, and attention. Our instruments become participants in the economy we're describing,
higher fidelity, higher price. Now keep the budget lens honest. FRBs aren't evidence of a simulation. They're likely magnetars and plasma doing hard, real work. But their rhythms hint at capacity edges. Repeating sources show activity windows, weeks of storms, months of silence. Some cluster near galactic centers, where magnetic fields and plasma density complicate propagation. The pattern looks like a system that accumulates stress, then vents quickly because slow leakage is expensive. That's not supernatural. It's efficient. Here's a micro-story. A night crew in British Columbia watches Chinese waterfall plots. A repeater they've nursed for a year erupts. 5 bursts in 10 minutes, each with different substructure. Slack channels fill. A VLBI network swings in. Timestamps align to microseconds. After dawn, the cross-correlation resolves a host dwarf galaxy with fierce star formation. The lead posts a plot. Arrival times versus frequency. A neat sweep. Someone jokes it's the universe zipping a file. Nobody laughs long. They're too busy tuning dead dispersion. What nobody knew at first was how FRBs would train us to think in buffers. You can't store everything, so you keep ring buffers hot and dump on trigger. You pre-compute dead dispersion trials. You chase latency out of the clock path. The telescope becomes a real-time decision engine, choosing which milliseconds to keep. That's the clue.
Programmer's dilemma written in sky noise, throughput versus fidelity. Keep more bursts with lower detail or fewer bursts with richer structure. Read the scene with the broader story. If bandwidth is finite, the universe may preload. Magnetars entangle energy in fields for years, then release it in ounces of time. Networks of observatories prime their buffers, then freeze frames on cue. The quiet nights aren't waste. They're the price of being ready when the spike hits. Interpret it carefully. FRBs point to a cosmos that prefers batching and bursts when the cost of continuous tracking runs high. If bandwidth is finite, the universe may preload scenes. Quantum shortcuts, entanglement, as non-local caching. We've been talking about bandwidth and budgets. Now, step into a lab where the universe seems to get a discount. 2 photons are born together, then fly apart. Measure one, you immediately learn something about the other. No signal crossed the gap. Nothing traveled faster than light, yet the results are correlated beyond what any local script could pre-write. That's entanglement. It doesn't send messages, it enforces consistency. Here's why this matters for our budget story. Bell tests took decades to close loopholes. Detector inefficiencies, timing windows, communication sneaks. Teams placed detectors in separate buildings, even separate islands, choosing measurement settings with fast random number generators while the photons were mid-flight. The correlation still violated Bell inequalities. They didn't know each other's questions, but their answers locked together. It's as if the universe stored a shared state that both measurements read from, not a conversation afterward. Think of it as non-local caching. In computing, you can keep a shared piece of state in a cache so different processors see coherent results without recomputing. Entanglement looks like that, with rules. You can't use it to shout across space. You can't flip a bit over there by choosing a setting here. But when both sides query, the joint answers respect a global ledger. The cost is paid in preparation and isolation. Maintaining that shared state is fragile and expensive. Action looks like midnight optics. In a city lab, teams send entangled photons down fiber to 2 rooftops kilometers apart. Detectors click. Each side's polarizer angle changes on the fly, driven by high-speed randomness. The timestamps have to be tight, nanoseconds, and clocks must be disciplined to a common reference. Then they do the math. The violation appears, small error bars hugging the line. It's a quiet thrill, not a magic signal, a constraint. The universe refuses a local hidden variable story. It prefers one that keeps a global pattern intact. Teleportation adds a twist. You can take an unknown quantum state here, and using an entangled pair and 2 classical bits, recreate that state there. Nothing physical travels except ordinary messages, yet the state reappears with fidelity set by the entanglement quality. It's not Star Trek. It's more like moving a file by sending a short diff, because both sides already share the big chunk. Pre-shared structure lowers the bandwidth of change. Entanglement swapping goes further. Entangle A with B and C with D. Measure B and C together the right way, and suddenly A and D, who never met, become entangled. The network gained a long-range correlation without ever touching the endpoints. That's a caching network,
stitching coherence across distance by consuming local resources at the junction. Every swap spends a fragile commodity, clean entanglement. Noise eats it, heat eats it, time eats it. What nobody knew early on was how engineering this would feel. Quantum repeaters aim to build an internet of entangled links. They buffer entanglement in quantum memories, purify noisy pairs by sacrificing some to fix others, and coordinate classical signals to say, use this pair now. Every step adds latency. Every purification costs yield. It's a balance between fidelity and throughput, the same dilemma we've been tracking in telescopes and data centers. Meanwhile, the no signaling rule stands firm. You can't beat light. The shortcut isn't communication, it's consistency. From our lens, that's cheaper. Keeping a global constraint satisfied can be less costly than letting everything diverge and then reconciling. Think of accounting. Double entry keeps books balanced at every transaction, avoiding massive audits later. Entanglement feels like double entry physics. Here's a micro story. Two groups coordinate an inner-city bell test using independent atomic clocks and GPS. A winter storm threatens fiber links. They switch to free space beams through clear air corridors. Temperature gradients jitter the path. Adaptive optics corrects the twinkle. The violation still posts. The relief isn't theatrical, it's practical. The consistency survived a hostile channel because the preparation was careful and the accounting was strict. Now zoom to theory.
Entanglement isn't a bonus feature. It's the glue of quantum mechanics. Many body systems use it to encode phases of matter. Error-correcting codes in quantum computing spread information across many qubits so local noise can be fixed without learning the message. Holography hints that space-time geometry itself could be sewn from entanglement patterns. In those models, connectivity, who's entangled with whom, shapes distance. The boundary code protects a bulk that emerges from relationships, not coordinates. Impact lands in two places. First, technology. Quantum key distribution, teleportation relays, sensor networks that beat classical limits. Each tool pays the same tax. Entanglement is hard to make, harder to keep. Second, interpretation. The universe appears to favor global bookkeeping over local narratives when budgets run tight. It won't let you exploit that to break causality, but it will use it to keep answers compatible. Read it with our thread. Local rendering versus global consistency is a trade-off. Entanglement looks like the universe pre-computing relationships, so later, measurements don't have to negotiate. That saves bandwidth on the back end by spending purity up front. When the environment gets noisy, coherence drains into heat. The cache invalidates. You pay with time to rebuild it. So, is this a glitch? No, it's the opposite. A stabilizer. But stabilizers expose costs. Labs chase picosecond timing jitters because if your stamps slip, your violation dulls. Fiber losses force repeaters to stack complexity. Every quantum network is a live demo of a rule. Consistency has a cost, paid in time. And as we'll see, when ticks themselves have a price, the meter is fundamental.